Welcome, physical science students. This is my first video for Chapter 3 on energy. Energy can be defined as an ability to accomplish change. When we think of the idea of change, it's not a really clear notion. So we're going to start this chapter by looking at what work is, power, and then different types of energy, such as kinetic and potential. Work is an idea that when a force is applied to something, a change will occur. That is the key concept for work. There has to be change. So if you apply a force to a table and the table isn't moving, you have done no work. We can calculate work by taking the force multiplied by the distance. In the top picture, you can see the person pushing on a brick wall. He is applying a force, but since the wall has not moved anywhere, in other words, distance equals 0, whatever force he's applying times 0 is going to be 0 work. Whereas the bottom picture showing force applied to a baseball and the baseball flying off into the air does accomplish work. New unit, our unit for work is going to be the joule after James Joule. And a joule is simply a Newton meter. Now the direction of the force when work is being done is assumed to be the same as the direction of displacement. If not, we can use a magnitude force subscript d of the projection of the applied force, as shown here. A force that is perpendicular to the direction of motion can do no work on the object. In other words, that means that gravity does no work on objects that are moving along the Earth's surface. If, on the other hand, we are lifting an object up into the air or dropping it through the air, we do have gravity involved because it's not along the Earth's surface. We will need to modify our work formula from force times distance and use mass times gravity times height. This is the work formula you will use anytime you're working against the force of gravity, either lifting or dropping an object. Our units are still the joule, of course. And keep in mind, if you remember from previous chapters, that mass times gravity is weight. So your work is the weight of the object times the height from which it is being either lifted or dropped from. If we look at a problem, we're going to calculate the work done sliding a box across a floor versus lifting a box up into the air. So our information here is the horizontal force of 100 newtons is used to push a 20 kilogram box across a level floor for 10 meters. How much work is done? And then the second part asks how much work is needed to raise that same box, 20 kilogram box, up by 10 meters. So the first part, we're simply sliding the box across the floor, and so work is force times distance. Our problem tells us that's 100 newtons of force. Plug that number in there. And we're pushing it for 10 meters, and you have 1,000 joules of work. That's the same as 1 kilojoule. So the mass of the box does not matter in this case because we're moving it along the Earth's surface. On the other hand, if we lift that box up, we're going to have to use this work formula, mass times gravity times height. So yes, in fact, the mass does matter when you lift an object up. So 20 kilograms was the mass. Gravity is 9.8 meters per second squared, and we're lifting it up 10 meters into the air. And look at our value here, 1,960 joules. It's nearly twice the work, which makes sense. Lifting something up in the air would require more work. It would be more difficult to do than sliding something across the floor. Now let's talk about power. Power is the rate at which work is done. And we can calculate power by taking the work that we just learned how to calculate in the previous slides and dividing it by how much time it takes to accomplish that work. Our unit for power will be the watt after James Watt, where a watt is a joule per second. Oftentimes power is presented as kilowatts, where 1 kilowatt is 1,000 watts. The British unit is the horsepower. Most of us are probably familiar with that. If you were to convert between horsepower and watts, 1 horsepower is equivalent to 746 watts. Let's do an example problem. A 15 kilowatt motor provides power for an elevator. How much time is needed for the elevator to go 30 meters to the 6th floor when its total mass, when loaded, is 900 kilograms? So in this case, we're solving for what is the minimum time. So we need to rearrange the power equal work divided by time and solve for time, which has been done right here. So time is equal to work divided by power. The next question we have to ask, well, are we doing work against the Earth's surface or against gravity? And in this case, an elevator going up in the air is going to be working against gravity. So we will have to substitute in mgh, mass times gravity times height, in place of work. And then power is on the bottom of the formula. So the elevator was loaded up with 900 kilograms of stuff. We're going to multiply that by gravity, and the elevator goes up 30 meters. That's your height. And then we divide it by power. Well, 15 kilowatts, we need to actually be in watts. So that's the same as 15,000 watts, which they have written in this example here, 15 times 10 to the third watts. That's just the same thing as 15,000 watts. And you do the math on your calculator and you get 17.6 seconds. Let's go back to this concept now of energy. Energy is the property something has that enables it to do work. So if you say that something has energy, it means that it's either able, directly or indirectly, to exert a force on something and perform work, perform change. So when work is done, energy is added to it. Our unit for energy is the joule, just as it was for work. Let's start out with our energy of motion. Kinetic energy, most of us have heard of before. Kinetic energy of an object depends on mass and speed. So our formula will be 1/2 times mass times velocity squared. Keep in mind that having a variable that is squared means that the kinetic energy will increase much more rapidly as speed does, or velocity does, compared to mass. So velocity has, in other words, velocity has more of an effect on kinetic energy than that of mass. We're going to find the kinetic energy of a 1,000 kilogram car when its speed is 10 meters per second. So here's our formula, 1/2 mass velocity squared. And the mass of our car is 1,000 kilograms. So you can plug that in there. And the speed, 10 meters per second. Do not forget to square it. So 10 squared is 100, or as they've written it, 10 times 10 meters per second. When you do the math here, you end up with 50,000 joules. And if you were to convert that to kilojoules, it's simply 50 kilojoules. Now think about if you doubled the speed or velocity. if this went to 20. All right, and if you put in 20 there and squared it, what do you think would happen to this value? We're doubling speed. Do you think that this kinetic energy would double? That's incorrect. It would go up 4 times, because when you double the speed, you have to double that. So 2 squared is 4. So our value would be 200 kilojoules. Potential energy, the energy of position. It is the idea of how much work something could do. In this example here, this person has raised a stone. It has potential to do work on the earth when dropped. So it has high potential energy here. Once that object is dropped and hits the ground, it has no more potential. Examples of potential energy would be a nail and a magnet. Once that nail has stuck to the magnet, there is no more potential. The same with our stretch spring here. We have potential to do work on what it is attached to, and then when it's just at rest, there is no potential. What we calculate for potential energy is something called gravitational potential energy, and it is the work an object can do if it is going to do work. So I didn't word that very well, I apologize. It's going to be the same formula as work done against gravity. Mass times gravity times height. Same formula. So an increase in potential energy of a raised object, such as this mass here, is equal to the work used to lift it. Well, the work used to lift something against the force of gravity is mgh. I will end our first video here, and I will continue on energy transformations in video 2 for chapter 3.